Good afternoon, class. We're continuing today with acid-base chemistry, picking up where we left off with example 3 on page 58, where we're going to be calculating equilibrium concentrations from initial concentrations. So first we have 2.1 times 10 to the negative 2 moles of hypochlorous acid dissolved in 15 milliliters of water. We're going to figure out what our equilibrium concentrations are and then figure out what the pH is of the solution at equilibrium. So first we have the reversible reaction. HClO and water reacts to form ClO- and H3O+ hydronium. This is an acid reaction, so we get a Ka associated with it, an equilibrium constant being equal to 2.9 times 10 to the negative 8th. So we can set up our Ka is going to be equal to our products over reactants, ClO- times H3O+ divided by HClO. Our initial concentration, indicated by the subscript I, is going to be equal to 2.1 times 10 to the negative 2 moles divided by 0.015 liters, which is our 15 milliliters of water, and that's going to be equal to 1.4 molar. That's the initial concentration of HClO. We do not have any of our products yet. All of the components are in a 1:1:1 molar ratio given in the equation, and so HClO- is going to go down by x as our two products each go up by x. So HClO is going to be equal to 1.4 minus x at equilibrium, and ClO- concentration is going to be x, and hydronium concentration is going to be x. This is the value that we are going to need for pH. So calculating x here is sort of the target for this problem. Now we can bring in our Ka expression and bring in our number, 2.9 times 10 to the negative 8th. That is going to be equal to our unknown product concentrations, x, at equilibrium divided by the equilibrium of our reactant. So x squared divided by 1.4 minus x. We have two methods to solve this. Our first method is going to be our shortcut. So first we're going to assume that we can ignore this x that's part of the expression 1.4 minus x. So we're going to say that 2.9 times 10 to the negative 8th is going to be equal to x squared divided by 1.4. And when we multiply both sides by 1.4, we get 4.1 times 10 to the negative 8th is equal to x squared. 2 times 10 to the negative 4th is equal to x. So to test, we need to make sure that that x is less than 5% of our 1.4. So we say 2 times 10 to the negative 4th divided by 1.4 times 100 ends up being 0.01%. So yes, we are absolutely able to take this shortcut here, and we do not need to do the quadratic. So we can move on. Now that we have our value for x, we need to figure out what our concentrations are at equilibrium. From our ICE table, our hypochlorite concentration and our hydronium concentrations are both equal to x, and our hypochlorous acid is 1.4 minus x. So earlier we were able to discover that we could just ignore that x because it's such a small value compared to 1.4. So we can just say that we have HClO is equal to 1.4 at equilibrium. So it's interesting because that is also the same as our initial, but turns out the change is so small that it really doesn't matter. You could prove this to yourself and do 1.4 molar minus 2 times 10 to the negative 4th, and you would find that you would round up to 1.4. So it would be the same amount. But those small values are going to help us calculate our pH. So HClO- or rather HClO is 1.4 molar, ClO- is going to be x, 2 times 10 to the negative 4th molar. Hydronium is also x, 2 times 10 to the negative 4th molar. And we're going to use that concentration, H3O-, to solve for pH, because pH is the negative log of hydronium. So pH is going to be negative log of 2 times 10 to the negative 4th, which is a pH of 3.7. That is less than a value of 7, which is neutral pH. So we can be confident that we have an acidic solution, which checks out. Before we move on to example 4, we're going to skip over to our empty notes page because we're going to include a little bit of information about the autoionization of water. So I wrote this on page 60. So the autoionization of water. This is an equilibrium between two equivalents of water and one equivalent of hydronium and hydroxide at equilibrium. The associated Kw, or rather the associated K with this reaction, is 1 times 10 to the negative 7. This is a very unique equilibrium constant that is only specific to water, so it gets its own unique name, Kw. Kw is equal to the hydronium concentration times hydroxide divided by the square of water. Water is a pure liquid and is not included, so 1 times 10 to the negative 14 is equal to x times x. 1 times 10 to the negative 14 is equal to x squared, and so x is equal to 1 times 10 to the negative 7. So what does this information mean? Well, to summarize, so far we have Kw is equal to the concentration of our acid and our base. And that is equal to 1 times 10 to the negative 14, setting equal to 1 times 10 to the negative 7 times 1 times 10 to the negative 7. What this means is that you have water floating around, and at any given point, you have a certain amount of hydronium and hydroxide in solution. They're very, very small amounts, but they're still present. You would never be able to tell that you have hydronium and hydroxide present when you're drinking it or experiencing water because it is such a low concentration that is completely negligible relative to the concentration of water in itself, which is something like 55 molar. Now that we have our concentrations of hydronium and of hydroxide based on water, we can then solve for the pH. So the pH is going to be equal to, is based on the hydronium concentration, which is equal to 1 times 10 to the negative 7th molar. So pH is going to be equal to the negative log of the hydronium concentration, and pH is going to be equal to the negative log of 1 times 10 to the negative 7, which is equal to 7. Now, just as we have the pH describing the hydronium concentration in water, we can also calculate a pOH describing the hydroxide concentration. So if we have the hydroxide concentration as 1 times 10 to the negative 7 molar, the pOH is going to be the negative log of that value, and pOH is going to be equal to the negative log of 1 times 10 to the negative 7th, which is a pOH of 7. Now, just as we were taking the negative log of hydronium and hydroxide to get the pH and pOH respectively, we can also take the negative log of an equilibrium constant like Kw. When you do that, a few really important relationships emerge. So you have, when you take the negative log of the entire Kw expression, you take the negative log of the left side, Kw, and you take the negative log of the right side, the product of the hydronium and hydroxide concentrations. Now, when you take the log of the multiplication operation, it becomes addition. So right here is a multiplication between hydroxide and hydronium. When we distribute, relatively speaking, and we separate and we get the negative log of hydronium and the negative log of hydroxide, that becomes a plus. So the negative log of Kw is equal to the negative log of hydronium plus the negative log of hydroxide, which we have just defined. So the negative log of Kw is the pKw. The negative log of hydronium is pH. The negative log of hydroxide, pOH. And we have just calculated that the negative log of each of these values in water is 7. We can add those two values together, 7 plus 7, to get a value for the pKw, which is equal to 14. So we can check this. The Kw for water is always equal to 1 times 10 to the negative 14. When we take the negative log of that, we get 14. So that checks out. So these relationships are very important because they are true for all aqueous ions, aqueous acids. So having the pOH plus the pH being equal to 14, we can always take that as being a constant relationship. So here we have 14 is equal to pH plus pOH. For water, that's 7 and 7. Now, I can summarize some of these relationships here. So we have the Kw is equal to the hydronium concentration times the hydroxide concentration. If we take the negative log of each of these components, we get down to 14 is equal to pH plus pOH. So for example, the negative log of Kw, the negative log of 1 times 10 to the negative 14 is 14. To go the other direction, we take 10 raised to these values to get back up to the top, so 10 raised to the negative 14. We can do the same for pH. The negative log of hydronium is pH, and pH raised to the negative, or 10 raised to the negative pH is hydronium. The negative log of hydroxide is pOH, and 10 to the negative pOH is hydroxide. Now that we have taken a look at the autoionization of water and brought out a few really important relationships, such as the 14 is equal to POH plus pH, and Kw is equal to the product of hydronium and hydroxide, we can return to example 4. In example 4, we have NH3 ammonia dissolved in 1 liter of water. At equilibrium, there are 4.4 moles of ammonia. What are the concentrations of ammonium and hydroxide, and what is the pH of the solution? So first, it's really important to identify what is an acid and what is a base in our reaction. So as we go from reactants to products, we can see that ammonia, NH3, gains a hydrogen atom and gains a positive charge. So overall, when you gain a hydrogen atom and a positive charge, you're gaining a proton. That is the definition of a Bronsted base. Similarly, you have water going to hydroxide, which is losing a hydrogen atom. You'll go from 2 hydrogen atoms to 1, and the charge is dropping. It's going from neutral down to -1. So this is a Bronsted acid as it is losing a proton. Water is acting as a proton donor. The Kb also gives it away. This is a base, so we have a Kb for our equilibrium constant, which is 1.8 times 10 to the negative 5. So we have Kb for our expression. That's always still going to be equal to products over reactants. For us, that's going to be ammonium, NH4 plus, times hydroxide divided by NH3. We can substitute in 1.8 times 10 to the negative 5th is going to be equal to our unknowns, x squared, divided by our known value for ammonia. Remember, there are 4.4 moles of ammonia at equilibrium, and we have 1 liter of solution, so our denominator is known, it's 4.4 molar. We can then easily solve for x. So we multiply both sides by 4.4, we get 7.9 times 10 to the negative 5th is equal to x squared, and the x is equal to 8.9 times 10 to the negative 3rd. Each of these values, ammonium concentration and hydroxide, are both equal to x, so both of them are equal to 8.9 times 10 to the negative 3rd. But it is the hydroxide concentration that is the most important to us. So far we've answered the first question. What are the equilibrium concentrations of ammonium and hydroxide? Done. We are now going to use the hydroxide concentration to figure out the pH of the solution. We can do that in 2 different ways. The first way, we can take the hydroxide concentration, calculate POH, and then calculate pH, and that's shown here. The POH is equal to the negative log of the hydroxide concentration, which is the negative log of 8.9 times 10 to the negative 3rd, which is equal to 2.1. We can then, from the autoionization of water, find that 14 is equal to pH plus POH. We have the POH is 2.1, and so we can calculate that the pH is equal to 11.9. In our second method, we can look at the hydroxide concentration, calculate the hydronium concentration, and from that, calculate pH. That's based on the fact that Kw is equal to hydronium, H3O plus, times hydroxide OH minus. So 1 times 10 to the negative 4 is going to be equal to our hydronium concentration times 8.9 times 10 to the negative 3rd, since that hydroxide concentration has already been calculated. Hydronium is then equal to 1.1 times 10 to the negative 12 molar. We can simply take the negative log of our hydronium concentration to get pH, which is the negative log of 1.1 times 10 to the negative 12, and we get a pH. So both ways, we were able to figure out that the pH of this solution is 11.9. That's going to be the end of the material for today. I didn't want to get too far into acid-base chemistry before the exam. On course, there's the key to problem set 4, and I wanted to draw everybody's attention to part B, where we saw the most difficulties. So this is a common ion problem, where you have something that dissociates completely to form 2 equivalents of the fluoride ion, 0.02 molar. So we have a common ion present, which is going to negatively affect the solubility of lead fluoride. Some people were solving this problem, including both the common ion effect and also activity. When you have a common ion present, it really does completely outrank any sort of activity. Now, this is all very messy here, but on course, I included what would happen if you were trying to calculate activity and the common ion effect simultaneously, which is not something that we've done in this class, but I thought I would include it anyway. But that's the end for today.